Alright, welcome to the playlist on vector calculus. The first video in this series is going to be dedicated to scalar and vector fields. So you might be wondering what vector calculus is really all about. And the first thing I need to do is introduce you to the concept of a vector field. But before we actually do that, we need to understand what a scalar field is. So just to give you a quick review of what scalars and vectors are, you remember that a scalar is just a number. It could be a number like 2 or 3. So it's just a number. That's all it is. It has no direction. It is just a magnitude. Whereas a vector, actually, it can be defined in multiple dimensions. So a vector can have multiple components. For example, in 3D, it has 3 components. So it would have Vx, Vy, and Vz. And the idea behind a vector is that it has a scalar quantity. All of these Vx, Vy, and Vz are all scalars. But basically, they're pointing in different directions. So for example, this one is pointing along the x-axis, this one along y, and along z. So when you combine this, the vector actually has a direction in all of the axes. And it is the combination of each of these quantities that gives you the total length of the vector. And we know we can find the magnitude of a vector simply by taking the square root of the square sum of its scalar components. Now, what is a scalar field? Well, it is just a function of multiple variables. If you recall from multivariable calculus, when you have a function of several variables, what you do is you're going to plot a point. So in this case, we have a two-dimensional function, which means it has points along x and y. So give it an input of x and y, let's say some point over here, and then this value here, so the function itself is going to give you another value, but this value is going to be along the z-axis. So for every value of x and y, you're going to have a value along the z-axis, which is defined by this function. So if I were to plot all those points, then basically we would have something like a paraboloid. So this is what a paraboloid looks like. It's kind of like a parabola but in 3 dimensions, and it has radial symmetry about the origin in this case. So you can imagine that every point on this function is just a scalar quantity. It is just a number that represents, and it has 3 coordinates. So having said that, what do you think a vector field is going to be? Well, it turns out a vector field, you're gonna give it a few inputs. In this case, we're gonna draw an analogy from the scalar function. We have 2 inputs, x and y, and this is going to give you a vector, and the scalar components of that vector are going to be defined by these functions. So the vector field is in itself a function that is a vector, and each of the points or each of the values of that field is going to be a vector in itself. So this sounds a little bit confusing, so let's just have a crack at this very simple example just to see exactly what I mean. So let's say we start off with f at 0, 0, so that would be the origin. Now if we put 0 and 0 here, then we have a vector that has 0 length, so basically this is nothing, it is just the origin. But how about I give you a point, let's say the point 1 and 0, which is basically over here. So we have 1 here and 0 along the y-axis. And now what's going to happen is this is going to be equal to the following vector. We're going to have 1 times I hat plus 0j hat. So what ends up happening is this is going to be a vector that has a length of 1 along the x direction. But now we're going to take this point here as the starting point of the vector. So what this is telling us is that the vector is pointing along the x direction, and it has a magnitude of 1 along that direction. So we're going to have the following. Let me actually draw it in a different color so you can see exactly what is happening. We're going to have a vector of length 1 along the x-axis, so it is going to go all the way to 2. So this is essentially the vector at this point. Now how about we extend this? Let's say I take another point. Let's say I take the point 2, 0. Then what are we going to have? Well, we're going to have this plus 0j. Alright? And now you start to see what's happening. You have a vector now that has length 2 along the x direction. and it has no component along the y direction. So now you're going to have a vector that is starting off at point 2, and it is extending 2 units along the x direction. So it is going along like this. So basically this vector is going to extend from 2 to 4. Just like that. So what's happening here is you're having your vector field. Your vectors are actually getting longer as you go away from the point 0 here, along the x-axis at least. Now you might imagine, well, what happens if we have points in this direction? Well, you can anticipate that the exact same thing is going to happen. If you have -1 here, then your vector field is going to give you the following vector. You have -1, 0. So now you have a vector that is pointing along the x direction, but it's going to the left. So it is also going to have a length of 1, because if you take the magnitude of this vector, it gives you 1. But now it is going to point to the left. So it is going to go from -1 all the way to -2. Right over here. And then the same thing is going to happen for this. So you can start to get an idea of what is actually happening here. So we're going to have another vector. Let me draw it for you. Another vector right here. And then these vectors are just going to keep increasing and increasing. Of course, there's going to be an overlap of those vectors, because if you draw a point, let's say halfway, where you could have something like -1.5 here, then you would have a vector that has a length of -1.5, but that is starting off at this point. So then you're always going to have that overlap. But in general, to visualize what is actually happening, we do this kind of thing where we just take unit-wise steps to see where the vectors are doing. Now, the same kind of thing is going to happen if you do it for the y direction. So let me just go down here. So let's say you take the following point. So let's say 0 at 1. Then what you're going to have is you're going to have 0 units along the x direction, and then you're going to have 1 unit along the y direction. So if you start off here, now you have a vector that is pointing 1 unit along the y direction, and it is just pointing straight up. So it's going to go from 1 to all the way to 2. So we have 2 here, and then if you do the same for any other quantity, so let's say the vector at the point 0, 2, you're going to have 0i plus 2j. So you have a vector that is starting off at this point, and it is now moving 2 units along the y direction. So it is moving straight up all the way to point 4. And you're going to have the same thing happening down below. So you start off here, you have a vector of unit length 1, then you start off at 2, at -2, you're going down all the way to -4. So let me just draw this here, -1. Here you have -2, -4, and so on and so on. So let's see what happens now if I take a point that is actually not 0 in either of the directions. So let's say I have a point like this, 1, 1. Okay, so we're going to have a vector that has a length of 1 along the x and a length of 1 along the y directions. So that gets a little bit more interesting, because now we're going to start off here, and then we're going to move 1 unit along the x direction to the right and 1 unit along the y direction straight up. So we're going to have a vector that looks like this. Now, if we take another vector, let's say we take the vector 2, 2, then what we're going to have is a vector 2 along the x direction plus 2 along the y direction, and this is basically going to start from this point here. So it is going to move 2 units to the left, to the right, and then 2 units up. So it's going to go like this. So we're going to have another point here, and then we're going to have a long vector. So you can see that the length is not going to be 2, it's actually going to be square root of 8. So these vectors and these magnitudes are going to increase the further away you move from the point. So you could say that this is just represents a radial kind of function. So it basically, the magnitude of the vector field is going to increase as you move away from the origin. And because of that radial symmetry, what you're going to end up having here is you're going to have a vector field that looks a little bit like this. So you're going to have vectors going off in all directions like this. So you're going to have another one here. And then if we draw the longer vectors starting at these points, we're gonna have that, then we're gonna have this here, and then this here, and so on and so on. And then you can draw vectors that go in between those two, and then you see that that kind of pattern is going to keep repeating in every direction. So this is the essence of a vector field. Each point does not give you a single scalar value, but rather a vector that has a direction and a magnitude. And it turns out that those magnitudes and those directions are going to keep changing depending on what point you choose. And the main question you may have in your mind is, well, what is the use of a vector field? I've never seen that being used before in any practical setting, but you'll be surprised because vector fields actually arise in two main fields. You have vector fields in fluid mechanics, and actually they arise in solid mechanics as well, but when you get to more advanced stuff, you're gonna see it. They definitely happen in fluid mechanics. In fact, this is essentially how fluid mechanics is formulated. And then they also occur quite a lot in electromagnetics. So electromagnetics deals with the propagation of electromagnetic waves across different media. And basically electromagnetic waves, they can be represented in terms of a wave vector. So a wave vector is actually going to be a vector that points in a specific direction. But not just that, you have electric fields and magnetic fields, which can also be represented in terms of vector fields, because the strength of the field changes with points in space, and it changes with direction. So there are a lot of effects that can be modeled by vector fields. Now, the final remark I want to point out in this video is that you may have noticed that for a scalar field, or just a multivariable function, when we have a function of two variables, we get a surface in 3 dimensions. But when we have a vector field, if we have two variables, or essentially two inputs, this only gives us a function that is a function on the xy plane. So there is essentially no third dimension here. And the reason for that, and you can pretty much test this yourself, I can just redraw this diagram here, is that if we were to draw this vector field on a set of x, y, and z axes, then you notice, well, all these vectors have 0 on the kth component, because essentially they are only defined by x and y components. So what you will see is you're going to have your origin here, and then you're going to have probably vectors coming off this way, and then coming off that way, and so on and so on. But essentially, this vector field is confined to the xy plane, because you won't really see any of those vectors coming onto the third dimension or the y-axis. And the reason for that is that in this case, you're just assuming that all the set components are 0. So in this case, if you were to have an actual 3-dimensional vector field, you would need 3 inputs. So it would be a vector field, or a function of 3 variables, so that you can have all those 3 components to define the vectors in 3 dimensions. And you're going to see there are really nice and really interesting properties that arise from vector fields, and those are the things that we'll deal with in this series.